Hey everyone. So first we will begin glycolysis and how it harvests pyruvate into acetyl-CoAs. There is an energy investment phase, which it operates anaerobically, so without oxygen. And then there's an energy harvest phase, which operates aerobically, which is over here. So we first rip off one part of an ATP molecule and attach it to glucose as energy investment. This makes a molecule that has 6 carbons, the glucose molecule, which is 6 carbons here, and we attached one of the phosphate groups over here. Over here, into the 6 carbon glucose molecule. This is called glucose 6 phosphate. Next, we are going to suspend another ATP molecule, have that phosphate group attached to the other side of the fructose 6 phosphate over here. So now we have 2. This molecule is very unstable due to phosphate groups being attached to each end, because if both the phosphate groups are high energy, the 6 carbon molecule will break in half, which is called a cleavage, creating 2 3 carbon molecules with a phosphate group on it, like so, over here and over here. The cleavage phase occurs right before it. These 2 cleaved 3 carbon phosphate molecules are called glyceraldehyde 3 phosphate. And making, we are then going to pull the energy off of the G3P using NAD plus and a phosphate group to make NADH, seen right here. But we're going to do this twice because there are 2 G3P. So NAD plus phosphate are put in, and then 2 NADH comes out. Then we're going to add 2 ADP to pull phosphate off of G3P, and then another 2 ADP to pull off phosphate from G3P. This ends up being 2 pyruvate molecules. So these steps right here, like I just mentioned, 2 ADP right here and 2 ADP right here, pulls the phosphate groups off to make 2 pyruvate molecules. In summary, at the beginning of the energy investment phase, we used 2 ATP molecules and made 4 ATP, as well as 2 NADH was made. But actually there's only a net of 2 ATP made because we used 2 at the beginning of glycolysis. This is the summary of glycolysis. Here is a better picture of glycolysis from one of my textbooks. Next, we're going to talk about pyruvate oxidation. A pyruvate oxidation occurs only in one reaction. We first put in coenzyme A molecule, which is going to join into the reaction. The coenzyme A, the CoA, will eventually attach to the pyruvate over here. The second thing is we're going to put in NAD plus and get out NADH, like so over here. In the process of doing these 2 things, we create a 1 carbon molecule. We create a 1 carbon molecule called carbon dioxide, indicated right here. The 2 carbon molecule with the coenzyme A, the CoA attached, is called acetyl-CoA. So the red star is the CoA, and then the acetyl is the 2 carbon molecule, which makes this a acetyl-CoA. But if you recall, at the end of glycolysis, we had 2 pyruvate molecules. At the end of pyruvate oxidation, we will have 2 acetyl-CoA and 2 carbon dioxide and 2 NADH made. For every glucose molecule, pyruvate oxidation reaction occurs twice. The 2-acetyl-CoA, we're going to break down the carbons one at a time and have it go around and around the Krebs cycle, which is indicated by these arrows over here. So in pyruvate oxidation, 2 NADH, in summary, is made. In the Krebs cycle, this is the third step. Acetyl-CoA first binds to oxaloacetate to make citrate first, right here. Second step is put in NAD plus to bring out NADH and release carbon dioxide, shown right here. It becomes a 5-carbon compound. Sorry, so I got kind of lazy, but this 4C means 4 carbon, and then this one dot right here is another carbon. So 5-carbon compound called alpha-ketoglutarate. Next, we put in another NAD plus over here and make NADH. This creates a 4-carbon compound and release a second carbon dioxide. This molecule is called succinyl-CoA. ADP comes in next, and our first ATP is formed. We make another 4-carbon compound called succinate. Then FAD comes in, which makes FADH2, which makes fumarate. NAD plus comes in and makes NADH, which makes oxaloacetate over here. Then we start the cycle over again when acetyl-CoA binds to oxaloacetate. We run the cycle twice because of 1 glucose molecule and the use of 2 acetyl-CoAs from pyruvate oxidation step. So in summary, 2 ATPs made, 6 NADH is made, and 2 FADH2 is made from the Krebs cycle, citrus cycle, TCA cycle. Lastly is the electron transport chain. So the purpose of this converter system is to harvest energy from NADH and FADH2 to build ATP. All the proteins involved in the electron transport chain are membrane proteins labeled 1, 2, 3, and 4. NADH is going to come in with its high energy electrons. It's going to bind to complex 1 and drop off its electrons. Electrons will go through a series of molecules and proteins going to complex 3. As electrons pass through complex 3, the hydrogen protons from the mitochondrial matrix, sorry I didn't write it here, but these are the protons, will go through, the hydrogen protons will go from the mitochondrial matrix through the intermembrane space and into the inner mitochondrial membrane. At the same time, the intermembrane space is being filled with more and more H plus protons to create a concentration gradient. The hydrogen protons want to go back to the mitochondrial matrix. Just think of the intermembrane space has more concentration compared to the inner mitochondrial membrane. So the H plus protons want to go back to the mitochondrial matrix, so they go through ATP synthase, which is this protein over here. Enzyme. Protein. ATP synthase job is to make ATP. ATP synthase is a rotary motor, which will jam ADP with energy from H plus to make ATP. In a perfect world, we can possibly make 30 NADH going through the electron transport chain and about 4 ATP using FADH. but relatively, they make about 30 ATP molecules per glucose molecule. Summary: about 32 to 34 ATP. They use up NADH and FADH2. Here are a better picture of the electron transport chain. And here is a summary of glycolysis, pyruvate oxidation, the citric acid cycle, and electron transport chain. 2 ATP, 2 ATP, and about 26 to 28 ATP is created. Per glucose, about 30 or 32 ATP is created. Thank you.